Now, let us prove the statements that we made in connection with the previous problem for the more general case. In the general case, we have this body occupying the volume V. Its boundary is divided into uh, delta Vt on which tractions are specified, and the rest is delta Vu. So delta Vt constitute delta V, and delta Vu intersection delta Vt is 0. So at any small element inside this dV, the strain energy stored per unit volume is half sigma ij epsilon ij for a linear elastic solid, where sigma ij and epsilon ij are stresses at this point, which we denote, let's say, by x with respect to some coordinate system. So this is the energy per unit volume, strain energy per unit volume. So this is the strain energy, total strain energy stored in this small element. Integrated over the whole volume, you get the total strain energy stored in the body. So this first term is the total strain energy stored in the body. In this, at this location, there's a body force, which is a force per unit volume. We have taken force per unit mass. So rho B is the force per unit volume. So rho B times dV is the total force total body force acting on this small volume. Integrated over the volume gives you the total body force. Similarly, rho B dot u, where u is the displacement vector of this point, which varies from point to point. So b dot u dv integrated over volume gives you the total work done by the body forces, potential of the body forces. So this can be written as in tensor notation. So this is the potential of the body forces. Similarly, these is the potential of the surface tractions which are applied on delta Vt. So total strain energy stored minus potential of body forces, potential of surface tractions, gives you the scalar called potential energy, which is a function of u. So this is a functional which contains u as well as derivatives of u, which are hidden here. And this is a function of three variables, and this is the function of three variables, which are the three components of the displacements, each of which are functions of three independent variables only. So this is a functional which depends on three functions, each of which are functions of three variables and their derivatives. Okay. On top of that, on delta vu, we have these essential boundary conditions also applied. So when we choose delta u, we'll choose it such that on delta vu, delta u are delta ui are 0. So for an we'll choose an isotropic material. So this is the constitutive equation for an isotropic material, and the strain displacement relationships, as we have discussed before, are these. So now what we are going to do is we are going to try and express this statement, the right hand side of this statement, completely in terms of displacement. So we will take these strain displacement relations and plug it in here. So epsilon, so we'll plug it in here to get, uh, this in terms of displacements, and we will use the constitutive equations to express these stresses in terms of displacements as well. So to do that, realize that sigma ij is 2 mu epsilon ij plus 2 plus lambda delta ij epsilon kk. So uh, this is times epsilon ij, and this gives rise to 2 mu epsilon ij plus lambda delta ij, and epsilon ij gives epsilon kk, and then you have let's say epsilon and then you have epsilon kk. So this is actually epsilon kk square, and this is epsilon ij square. So this, the first term will become mu times ui comma j plus uj comma I whole square, and the second term will become u k comma k whole square. Okay, so this is how this term is expressed in terms of displacements. This term is expressed in terms of displacements. So this whole expression now becomes in terms of displacements. This is how you get it. Now you have to do delta u, and to do delta u, let's do it for this term first. So I have mu by 2 ui comma j, which is derivative of ui with respect to j, plus uj comma I whole square, and I want to take delta of that. So I'll get mu ui comma j plus uj comma I times delta ui comma j plus delta uj comma I. Okay. Similarly here, for this term, these two are basically the same. They are repeated indices, so they are the sum of the diagonal components of the displacement gradient. So when you take delta of that, this is what you will get. This, of course, you will get only delta ui, and here also you will get only delta ui. Ti would remain as it is, bi would remain as it is, because these are not functions of displacement. So if you perturb the displacement, uh, bi and ti don't get perturbed. Now here you have derivatives of the variation, derivatives of the first variation of ui and uj. So you need to get rid of the derivatives. In order to get rid of the derivatives, we again use the divergence theorem, which is in 1D we use the integration by parts. In multi-dimensions we use the divergence theorem. So you have del uij u. So let's just take this term into this term. The other, this term into this term can be done in a similar way, and this term into this term can be done in a similar way. So let's do it for only one case, and this we can, the whole thing we can write in this manner. So you can write it as del ui comma j plus uj comma I whole derivative with respect to j minus delta ui so this term can be written as this term minus this term. Okay, both contain del ui, and then to the first term you can apply the divergence theorem, and it becomes integral over the surface, and you can write it as del ui comma j plus uj comma I in j ds minus the volumetric term remains. So this comma j, this term remains. Similarly, you can do it for this also. So v del ui comma I uk comma k dv that you can write as you have derivative with respect to I, so you can write it as del ui uk comma k comma I minus del ui uk comma ki. So this is how you can write this term, and then applied divergence theorem here, this converts to a surface integral, and that surface integral would be del ui uk comma k ni ds, and this volume integral will remain. This volume integral. Now putting all the volume terms and the surface terms together, so this is del pi, which is equal to 0, which we have to set to 0. These are the all volume terms put together, and these are all the surface terms. Now let us take the constitutive equation. The constitutive equation was 2 mu epsilon ij plus lambda epsilon kk delta ij equal to sigma ij. So from here, we again express this in terms completely in terms of displacement. So we write mu ui comma j plus uj comma I, replace the strains, and then epsilon kk is uk comma k. So we write uk comma k delta ij equal to sigma ij, and therefore taking this and plugging it here, this is actually sigma ij. So what you have here is sigma ij nj over the surface, part of which it's the entire surface delta v, but you also have this del ui, which is equal to 0 over delta v u. So over delta vu, this quantity is 0. Over delta vt, this is not 0, but this is equal to the traction ti. So you actually reduce this second integral to second surface integral to integral over delta vt, where this is equal to ti delta ui ds. So we also have this term, which is the applied traction. So what we can write is on delta vt, you have del ui ti minus ti hat ds, and this whole thing is equal to 0, which means that this term has to be 0 separately, because delta ui as usual is an arbitrary function. So this equal to 0 gives you what is known as the Navier's equation. Recall that Navier's equation of elasticity is the equilibrium equation with the strain displacement relations and the constitutive equation for an isotropic elastic solid, all rolled into one. So this pertains to an isotropic elastic solid for small deformations where the strain is given by half ui comma j plus uj comma I. That gives you the Navier's equation when you plug these things into the equilibrium equation. So this has to be valid at each and every point. This differential equation has to be valid at each and every point. And the natural boundary condition on delta Vt, this has to be 0 as well. And this means that Ti has to be equal to the applied traction on delta Vt. So this completes a proof of the fact that if you start with the general potential energy expression for potential energy of an elastic solid, isotropic elastic solid, you actually end up the Euler's equation corresponding to that, the Euler-Lagrange equation corresponding to that is actually the Navier's equation. So the Navier's equation, solving the Navier's equation for ui is exactly equivalent to finding a u which minimizes this potential, which represents the potential energy of the body.